Here's a problem I made up, and it's y double prime minus 7y prime plus 10y equals to 4 cosine 3x. Now this would match case 4, bottom of page 276 in this book, and where it deals with cosines and sines on the right side. To apply a linear operator the way we've been applying it, in other words, if we were to say y particular is equal to 1 over d squared minus 7d plus 10, operating on 4 cosine 3x. Our problem is that this is going to turn into some kind of infinite series expansion, and when you start taking derivatives of cosine, you'll end up with an infinite series expansion. You'll get an infinite number of cosines and an infinite number of sines. It seems unlikely that that would be productive. That would probably not even converge. So I think that approach is either impractical or it just doesn't work. I haven't explored it with this problem. I have with a different problem and got a pretty interesting result. I may share that with you in another video. But in any event, this approach is not very productive. However, we're going to pull one of the tricks out of our bag and solve an alternate problem. Y double prime minus 7y prime plus 10y equals to 4e to the 3x. Oh, sorry, that's not quite what I meant. 3i times x. So I'm using the Euler equation, or Euler formula, where you have e raised to an imaginary power there. This would be the 4 on the outside, times the cosine of 3x plus I times the 3x, sine of 3x. So this expression contains 4 cosine 3x. All right? And in fact, it's the real part of this expression contains it. Now, if this was equal to 4 sine 3x, then the imaginary part contains 4 sine 3x. So in this case, because it's the real part containing it, when I work this problem, I'm going to use the real part of the answer. And let's do that. I wrote out y particular, which is going to be the polynomial operator, d, in the denominator, d squared minus 7d plus 10 is in the denominator. Of course, this appears in the numerator. So I'm taking 1 over this polynomial operating on 4e to 3ix. All right. Well, in the last video, there was this wonderful theorem, and I'm going to write it back on the board here. It was y particular, if it equals to 1 over a polynomial operator operating on be to the ax, then we can rewrite this as be to the ax over pa. And that's, if you're using this book, that's on bottom of page 275. It's sort of a simple version of the exponential shift theorem for inverses. Okay, it's a theorem in its own right. And so I'm going to literally just plug it in. So this would equal to, and we just take this expression and rewrite it in my numerator, 4e to 3ix. And then it's over this polynomial evaluated at a, coefficient a. Coefficient a is not 3, it's 3i. So careful there, it's 3i. So I'm going to replace the d's with 3i. So 3i squared minus 7 times 3i plus 10. And we'll work that through. That's 4e to 3ix over, this would be 9i squared. 9i squared is going to be minus 9. Minus 21i, and then plus 10. So y particular for this equation right here, not the top one, but this equation, y particular would be equal to 4e to the 3ix over, and like I said, I squared is -1, so this term is minus 9. So I have 10 minus 9 is 1. 1 minus 21i. Great. Now, from here, it's, that's the easy part. Now it's the messy part. Okay. First of all, I think the best thing we can do is to rationalize the denominator. In other words, get rid of the complex number in the denominator. And we do that by multiplying top and bottom by the conjugate, 1 plus 21i. Alright, so on top, I'm going to keep it factored on top for now. So I have 4 parentheses, 1 plus 21i, e to the 3ix. Down below, we have, for all this out, we have 1 plus 21i minus 21i. And then minus 21, oh Lord, 21 is, squared is 441, I believe. Minus 441 I squared. And then this becomes a plus 441, and those terms cancel, so I have 1 plus 441 is 442. 442. There we go. So now I'm going to use Euler's formula here, and well, we have big numbers, but hey, we got calculators. So I'll do some erasing and we'll wrap this up. We were left with, I erased my y particular here, but y particular was equal to this expression. I reduced the fraction, it's 2 over 221. And then here's 1 plus 21i. And then we expand the e to the 3ix using Euler's formula as cosine 3x plus I times sine 3x. And then we get to multiply all that mess together. So it's 2 over 221 times, okay, here I've got cosine 3x, and then that was this term, these terms multiplied together. And now I'm going to do the last terms, because this is going to be plus 21i squared sine 3x. And I separate those because this will be the real part, since I squared is -1. And then, just for the record, we have the imaginary part. We have I, 21 cosine 3x, 21 cosine 3x, plus I times sine 3x, plus sine 3x. So here's my I factored it out. Let me erase this little part here. So the real part is up here because this becomes a minus 21. The I disappears, the I squared disappears rather. And so here's the real part, here's the imaginary part. Since I'm working with cosine, the original y particular that we're really solving for is going to be 2 over 221 times the real part, parentheses, cosine 3x minus 21 sine 3x. There we go. So now if this had been for sine 3x instead, our answer would have been close. It would have been 21 cosine 3x and then plus sine 3x. So these would have reversed a bit. Alright, so that's how you do a sine or a cosine problem like that. At least a simple one.